Okay, let's take a look at these other types of equations now in this section 1.6. We're going to look at 4 different types of equations. We're going to look at rational equations, equations that have radicals, equations with rational exponents. Remember, rational means fraction, fractional exponents, and equations that are quadratic in form. So let's begin with first working or solving rational equations. I'm going to make up an example here, a simple example. Suppose I have 3x minus 1 divided by 3, negative 2x over x minus 1 equal x. So this is called a rational equation because we have a fraction and the variable appears on top as well as on the bottom of a fraction. All right, it doesn't have to necessarily be like that. I could have 1 over x plus 1 over 7 equal to 5. That's also a rational equation, as long as x is in either top, bottom, or both. Okay, so there we have this rational equation. So how are we going to solve this? Now, because we are allowing variable in the denominator of this fraction, we need to declare the domain before we actually solve this. So the domain of this expression or equation is going to be anything but 1, right? X cannot be 1 because you get division by 0. For all rational equations, the domain is all real numbers, except what makes the denominator 0. All right. Now, there are a couple of ways of solving these rational equations. One way is to identify the LCD. So here you go. The LCD is 3x minus 1. Remember, for all denominators. Even on the other side, sometimes we have a fraction. This time we don't, so the denominator is 1. So we want the LCD of 1, x minus 1, and 3. The smallest, the least expression that's divisible by all 3. It's going to be this. All right. Now, once we have identified the LCD, the next step is to actually build each fraction to the LCD. So that's what I'm going to do next. Here's 3x minus 1 divided by 3. Next, I have negative 2x over x minus 1 equals x. I'm going to give x a denominator of 1. Notice what we're doing. We're doing to both sides. We're going to build to LCD. So for the first fraction, it has 3. It needs x minus 1 to become the LCD. So multiply top bottom by x minus 1. The middle fraction, x minus 1, the denominator, it needs a 3. Multiply top bottom by 3, so its denominator is also LCD. And for what's on the right side, the fraction on the right side, this one needs both 3 and x minus 1 to become LCD. And there you have that one. Now, once we have built everything to the LCD, we can simplify it. 3x minus 1. 3. You see how all denominators are the same? No surprise, because that's what the intent was. Now, first fraction numerator, we got to FOIL this. So I'm just going to do the FOIL. We've been doing many of these, so you can follow the work. 3x squared, negative 3x minus x plus 1. There's my FOIL. The middle fraction, 2 times 3 would be 6x, and on the right side I have 3x times x minus 1. That's 3x squared minus 3x. Good. Now, because all denominators are the same, at this point we could combine these two fractions with a common denominator, and we can equate it to the equation on the right, the expression on the right side, And because the denominators are going to be the same, we can simply, once all denominators look the same, you can simply drop the denominators. And when we do, we're just going to end up with the numerators as 3x squared negative 4x plus 1 minus 6x equal 3x squared minus 3x. You see how that worked? Just drop the denominators. And then I'm going to combine like terms. That's 3x squared negative 10x plus 1 and 3x squared minus 3x. And then we're going to solve this. Let's isolate x on the left side. So I would subtract 3x squared from both sides. And when we do, those cancel. So I'm going to have just negative 10x plus 1, negative 3x on the right side. Next, let's add 10x to both sides. This way I have x with a positive coefficient on the right side. And divide by 7. So there is a solution. The solution x is equal to 1/7. And 1/7 is in the domain. It's one of many values that are permissible. The only thing that couldn't be is 1. Now, what if we solved and actually this turned out to be a 1? It didn't. But what if it ended up being what was not in the domain? Okay, in our domain, remember we said x cannot be 1. Oh, hold on, let me align things back on. Okay, sorry, I don't know what happened. All of a sudden things went crazy. But there we go. What if the solution ended up being 1? Well, in that case, if the only solution we had was 1, at that point we just called it no solution because it's not in the domain. And that will happen sometimes in our examples that we do. Okay, so there is a solution to that one. Now this was method 1. So remember, method 1, you identify LCD and you build both sides to LCD. Now let's look at our alternate method for this one. Okay, the alternative method, call this method B. See which one you like better. Method B or second method, call it method 2. 1, 2. So this is the second method. And the equation was 3x minus 1 over 3. And negative 2x over x minus 1 equal x. Just like previous method, we're going to find the LCD. The LCD is 3x minus 1. Now here's how this is different from the first method. Once we identify the LCD, we're going to actually multiply now both sides by LCD. So I'm going to times this by 3 times x minus 1. I'm going to multiply the left side by 3 times x minus 1. Okay. Now, once we have that, then we're going to multiply both sides. And multiplying both sides by 3x minus 1, 3 times x minus 1 times the first fraction. All the 3's cross out. So we're just going to get, we're just going to get x minus 1 times 3x minus 1. Correct? And then we're going to do it again to the second fraction. Here's LCD. We're going to multiply by this fraction. When we do, the x minus 1's now cross out. So that's just going to be 3 times 2x. Correct? And on the right side, we have 3x times x minus 1. It becomes 3x squared minus 3x. Distribute to the right. And there you go. Notice, if we do this correctly in one step, we can eliminate fractions in one step. Now let's do FOIL here and see what happens. Let me see. Okay. When we FOIL, we're going to get 3x squared minus x right? 3x squared minus x, negative 3x plus 1 minus 6x equal 3x squared minus 3x. And then we can combine like terms. Combine like terms on the left, we get 6, 9, and 10, negative 10x plus 1 equal 3x squared minus 3x. Now, if you look at the expression here and the expression that's up here, if you look at those two, they look exactly the same. See these two? They look identical. More like this one, right? But they're the same. So again, both of them do the same thing. The reason is because the first method we dropped the denominators. The second method we didn't drop them, they just disappeared themselves. In fact, this is the reason for why we dropped the denominator in the first method, because the next step would be to multiply by LCD and they'll go away. Now, just as before, the 3x squares cancel, add 10x to both sides. And this is going to be 1 equals 7x. And from this, x is 1/7, just as before. So with rational expressions, again, two ways you can do this. Personally, method 2, I like it better. This one, where we multiply both sides by LCD. That's just my personal preference. Okay, what if we have, let's do another rational expression in this example. So this time, suppose I have 3x plus 2 divided by x minus 2 plus 1 over x equals negative 2 divided by x squared minus 2x. Okay, what if I have that one? So first, remember, we need to declare the domain, and domain is all real numbers except what makes the denominator 0. X minus 2, 2 makes that 0. So we're going to exclude 2. Denominator of just x, 0 makes that 0. And x squared minus 2x, what makes this 0? Let's factor it. GCF is x, we get x minus 2. And notice they're the same factors as the ones we just considered. So this is the domain. Anything but 2 and 0. Now let's solve this one. I'm going to go ahead and use method 2 in that I'm going to multiply both sides by the LCD. So the LCD is going to be x times x minus 2. Remember, LCD is for this denominator, this one, and this denominator on both sides, not just on the left side. And in order to find the LCD, if the expression is not in factored form, we gotta factor it, because that's how we identify the least common multiples, or GCFs. In this case, the LCD, the least common multiple. All right, now I'm going to multiply both sides by x times x minus 2. So that's going to be 3x plus 2 over x minus 2, 1 over x, and on the right side, negative 2 over. I'm going to write the factored form of the denominator on the right side. See that? The factored form. We're going to multiply it also by the LCD. All right. Now what's going to happen? When we distribute LCD to the first, LCD to the second fraction. First distribution, the x minus 2 crosses out. So this is just x times 3x plus 2. Second distribution, the x crosses out in the second fraction. That's going to be x minus 2, right? That's the only thing that distributes, because the x cancels. And on the right side, x and x minus 2, that is the LCD. So all you have is negative 2 on the right side. Now we can remove parentheses. That's multiply x by binomial. Remove the parentheses on the second binomial. I'm going to go ahead and bring negative 2 on the other side. make that positive 2, so I have 0 on the right side. This is going to be 3x squared plus 3x. 2 and minus 2 are 0. And there you have it, which is nice. We can now solve this one. And to solve this, we can factor the GCF, leaving me with x plus 1, and solve by zero factor principle. By zero factor property, 3x could be 0, or x plus 1 may be 0. Divide both sides by 3 and x is 0. Subtract 1 in the second one and x is negative 1. So we have 0, negative 1, as at this point these are potential solutions. I'm going to go back up here and look at my exclusions. Remember, 0 and 2 are not allowed in the original. And again, the reason they're not allowed because 0 in the second fraction give me 1 over 0, which is undefined. All right, and check out what we got. We have 0 in a solution, therefore we need to exclude that or discard it. We simply discard or omit this one. So the only solution, our final solution, is going to be negative 1. That's the only one that works. And as always, you can check the solution just to make sure that it works. I feel comfortable the way we did this, so we'll leave that check for you if you like to check it. And there you have it. Okay, so that was example. Both of these are example of rational equations. Now, let's take a look at, besides rational equations, I said we want to look at equations with radicals, rational exponents, and quadratic in form. Okay, let's take a look at radicals, equations with radicals. So, this time, radical equations. Let's say we're going to start by something simple. The root x equals 5. Now, if square root of x is 5, remember the square root, this means positive root. The square root symbol stands for positive root or principal root. Now, square root of x equals 5. Well, to solve this, we can square both sides. And x becomes 25. Now, for radical equations, we always check solutions to radical equations. And the reason is because sometimes when we do this business of squaring both sides, what happens is that we create extraneous solutions. Okay, what I've done here, by the way, is called the power property. Let me write this. The power property of equations. Okay, the power property of equations says that if we have two algebraic expressions, okay, so let's say if P is equal to Q, then we can raise P and Q to same powers. So P to the n is equal to Q to the n. Okay, here, Q to the n. Now this expression is in the form of if-then. That means it will for sure work from left to right. If this presupposition is true, then the conclusion would be true. All right, so for example, to show you an example illustration of this one. Let's say I have 3 equals 3. Now if I square both sides, I get 3 squared equals 3 squared, 9 equals 9, it checks. You see that? But going in this direction, not always true. It's not necessarily true. And here's what I mean. Suppose now I have, let's say my P and Q are like this. Let 4 squared be equal to negative 4 squared. So here's my p, there's the q. Now that clearly is a true expression, right? 4 squared 16, negative 4 squared 16. So that I'm starting with the right statement. So I'm going from right to left now. Can I imply here, does that imply that 4 equals negative 4? That's not true, is it? So for that reason, because this is not in the form of usually if and only if statements work both ways. This is the form of if then, which is an implication. It's not a bidirectional implication. So it only works in one direction. For that reason, remember to always check the solution to radical equations, especially when you raise them to even powers, because things like what I just said here, things like this do happen in our work. All right, now let's take a look at another example. Let's say this time I want to do x minus square root of 15 minus 2x equals 0. Now for this one, I can move the radical. Oh, we can raise both sides. Usually to get rid of square roots, we square both sides. But we don't want to square them right now yet. And the reason is this. If I do square both sides, there you go. We could. They cannot prevent us from doing it, but we don't want to do that. And here's why we don't want to do that. It's because when we square the left side, the right is just 0, but the left side, when we square the left side, it's a binomial. So it's going to be x squared, negative twice first by second, plus second one squared. Now the second one squared is the radical. This is fine. That's just going to be 15 minus 2x. When you square root of something, you just lose the radical. You get the radicand back. So that's going to be 15 minus 2x. But see the trouble? Now I have more complicated expression. So we're not going to do that. Okay, we're just going to stop here. That's why it's too early to square both sides. So what we want to do is we would like to, first we want to isolate the radical as much as possible. That's what we would like to do. So to isolate the radical, I'm going to move it simply to the right side. Now I can square both sides. See, if I square it now, I'm squaring a single term on the left, a single expression on the right, and it will do what we expect it to do. Perfect. And the radical is gone. All right, and we can now solve this by solving quadratic equation. If I bring the terms on the right to the left side, they become that. And now, will this be factorable? I hope so, so I don't have to do quadratic formula. If something is not factorable, usually we use quadratic formula. You could complete the square, but to me quadratic formula is like the elephant gun. It's just gonna put any quadratic equation out of its misery. It's just gonna solve it. So that would be my personal preference. If something is not factorable, I use quadratic formula. So this one is going to work out, and the solution, negative 5 makes first, 3 makes the second binomial 0. So those are two solutions. Now, with radical expressions, the domain, we always have to worry about domain when we solve equations, because we could get numbers that when we plug in will not work. So let's do the domain of this radical. Domain of all radical expressions, square roots that is, or any radical, is where radicand is defined, where we can actually take the roots, whether it's square root, cube root, fourth root, whatever. Now our work is primarily with square roots. So in order to determine the domain of radical expressions, or like that one, square root, this is the radicand, domain is where radicand has to be at least 0. So in the case that we are working 15 minus 2x right up here, that's our radicand. That's going to be greater than or equal 0. Now if I subtract 15 from both sides, and remember, add and subtracting to an inequality doesn't change the direction of the inequality. Then divide by -2. If I divide by a negative and multiply by a negative, we have to change the direction of inequality. And there you go. That's what we call the implied domain of radical. As long as we have numbers that are less than 15 halves, this thing is going to work. Okay, now 15 halves, 7.5, and in this case, 3 and -5 are going to work, right? In here. Here's my domain. Here's 0. This is 15 halves. See our numbers. One of them was -5. The other one was 3. There you go. Both of these numbers are in this infinite domain. So we're good with this one. And there we have the solution to the radical expression. Hopefully I did this correctly, and I think if it looks good, I feel good about it. So there we have the solution. Now sometimes we have more radicals, like we could have 2 radicals on either side, and again, these can get fairly complicated, but we're just going to stay with the example I just gave you. So let's take a look at now another example of the types of equations we work at. Let's say I want to do now with a rational exponent. Rational exponents. Okay, with rational exponents, so an example would be this. Now let's say I want to do x to 3/5 equal 27, something like that. Okay, now when we work with rational exponents, then we can use the power properties, right? By raising both sides to a power. Now the power that we want to raise to, because these are fractions, rational means fractions, we want to raise it to the reciprocal. Usually we raise it to the reciprocal of the fraction. Okay, now let's remember the reciprocal of the exponent. That's what we want to do. Reciprocal of 3/5 is 5/3, so I'm going to raise both sides to 5/3 power. Now the original expression, by the way, x to 3/5, remember that's going to be the 5th root of x cubed, like that. And because the index is 5, there's no restriction on the radicand. So domain here is all real numbers. There, all real numbers. Because we are allowed to have, for example, cube root of -1, 5th root of -1. Those are okay. Both of these happen to be -1. Okay, now x to 3/5 to 5/3 reciprocals multiplied to 1. Next in here, we're using the power rule of exponents, right? The rule we use here is this: a to the m to the n is a to the mn. That's the one. 27 to 5/3. Well, the expression here we have is the following. If you recall, when we have a to the m over n, we can write this as the nth root of a, the whole thing to the m, or the nth root of a to the m in that form. So I can write 27 to 5/3 as cube root of 27 quantity to the 5th. So I'm going with the first option, because I can take the cube root of 27. See, that's just 3, and then do 3 to the 5th power. And I believe 3 to the 5th power, that's 3 by 3 by 3 by 3, 9, 81 by 3, 243. There you go. Our domain is all real numbers because index is odd, and that's going to work out. So remember, with rational exponents, you want to raise it to the reciprocal of the exponent, and that should take care of it. How about, what if I have something like, let's make this one up. What if I have a binomial? Let's say x minus 4 to 2/3, make that equal to something that will work nicely, 16. Okay, so we're going to raise both sides to the reciprocal of the exponent. So I'm going to raise to 3/2 power. Doing so, we get x minus 4 to 2/3 raised to 3/2. And on the right side, we have 16 raised to 3/2. The left side is the easy side, actually. See, because reciprocals multiply to 1. And the right side, I just have square root of 16 cubed. Remember, when the index is 2, we don't write it. So 16 to 3/2 is index 2 of 16 cubed. But then index 2 is simply square root, which we don't write. That's how I got square root of 16. It's like, where did the 2 go? It's there, but we don't write it for square roots. Square root of 16 is 4. 4 cubed is 64. Add 4 to both sides, we get 68. And there you have it. Now, because initially we have cube root, right? 2/3, the denominator is the index. So this is a cube root. Therefore, the domain is all real numbers. Again, for this reason, because x minus 4 to 2/3, that's simply cube root of x minus 4 squared. See that? As long as the index is odd, there's no restriction on the domain. Therefore, 68 would be the answer on this one. All right, let's do the last type of equations here. So I'm going to talk about equations that are quadratic. Let me put equations that are quadratic in form. Quadratic in form means if we rewrite it, we will see explicitly, we can see a quadratic equation underneath the equation that we're looking at. Okay, so what is quadratic in form? An equation that can be written in this form: au squared plus bu plus c equals 0. This is in quadratic in form, where u here, remember, a can't be 0. So if a is 0, we don't have a quadratic. That's why. So a can't be 0. And u here, u is an algebraic expression. Okay, so u itself is an algebraic expression. So this is called quadratic in form. So let's take a look at an example. For instance, let's say my expression is, suppose I have x plus 1 to 2/3, and then x plus 1 to 1/3, and I'm going to go, let's go -2. This should work. Okay, I want to solve this one. Now notice I have an expression in x, namely x plus 1. The whole equation is a rational equation. Okay, I mean the rational expression on each of the terms, and this is what we call a quadratic in form. To see the quadratic in form, I'm gonna let u be, and for most parts, so like, how do you know what to let this variable u be? The middle term is what we usually let it be. So I'm gonna let u be x plus 1 to 1/3. Okay, well, if u is that, then what will u squared be? If I square both sides of this one now, I'm going to get x plus 1 to a third squared, right? And that's going to be x plus 1 to 2/3. And that's actually good, because if you look at now first term and look at that one, isn't that u squared? So the next step is to rewrite x plus 1 to 2/3 as u squared minus u minus 2 equals 0. And that fits the definition of quadratic in form. Now that we have this, notice, so underneath the equation, what seemingly was rational exponent, there lies a quadratic equation. Now we can solve this one. Most of these hopefully are factorable, so that we don't get bogged down with all the details of solving these. So there you go. This should be factorable. -2 times 1, -2, -2 and 1 makes -1. The middle term, the coefficient is -1, and we are good. From this, u is 2. From this, u is -1. Okay. Now, next step, because we started with variable x, we're going to finish the answer to x. These are answer to u's, not to the x's. So, what do? We go back to what we let u be. 2 is equal to x plus 1 to a third, and -1 equals x plus 1 to a third. And to solve this, we can now raise both sides, cube it. Remember, you raise it to the reciprocal of exponent. Reciprocal of 1/3 is 3. So on the left, 2 cubed is 8. To the right, we just get x plus 1. -1 cubed, -1, to the right is x plus 1. Subtract 1 from both sides, and we get x is -2. Subtract 1 from both sides, x is 7. And there we have it. So we found two solutions to this equation. Again, what's the domain of this one? Because the original problem is 2x plus 1 to 2/3. So this is cube root. And let me just say domain again is all real numbers. It's very important that we declare the domain in every equation, because sometimes we do come across where the values are not in the domain. When you solve them, I call them potential solutions. When you check them and they work, they become these solutions. And there you have this one. Let's take a look at another example. What if this time I'm going to go 6x to -2 plus x to -1 plus, let's go -2. -2 equals 0. Okay. Now for this one, again, I'm going to let u be the middle term, the variable in the middle. Now, if this was like 5x to -1, you don't need to let u be 5x to -1, only the variable portion. And if that's the case, when you square u, you'll be squaring x to -1 by the power rule of exponents. That's x to -2. And look at that and this one. They share the same variable, the first term. So I'm going to rewrite this as 6u squared plus u minus 2 equals 0. And for 6u, let me go 3u and 2u. That gives me 6. -2. Let's go -2 and 1. Will that work? The product's -2. Let's do the OI. That's the OI combination in FOIL. -6 and 2, -4. Nope, that's not going to work because the middle term is just u, means 1 positive u, this one. So the OI combination, I'm going to change this to a 2 and the 2 to a 1. So here's 6u squared, that's -2. We got the first and the last, the O and the I again. Outside, inside terms, or outer, inner terms. Those are going to be 4u minus 3u, that's u. Perfect. This should work. each factor, next the zero factor property kicks in. Each of those factors may be 0, and we pick up u half in here, 3u negative 2, and we pick up ub negative 2/3 over here. Again, we're not done with this because this is a solution for u. We need to solve for x. Oh, domain, that's very important. Because we have negative exponent, x to negative 1. Now, negative exponents, remember, we can rewrite them with positive exponents. X negative 2 is 1 over x squared. In both cases, the only place we have trouble here is when we have division by 0. That means when x is 0. In both cases, in both fractions. So x cannot be 0. Anything else, if we solve it and it works, then so be it. Now let's go back to remember what we let u be. And we're going to plug in u into that equation. Negative 2/3 equals x to negative 1, which I just mentioned, that's 1 over x, right? Over here, using negative exponent rule. And we can do one of two things. Let me just show you. We can flip both fractions. If we flip them, then we get negative 3/2 equals x over 1, which is just x. And there, we solved it. X is negative 3/2. Or we can cross multiply because we have a proportion. Remember, this is a proportion. A proportion is equality of two ratios. So with proportions, we can cross multiply, right? Remember, a over b, c over d. Has to be an equation so we can cross them. Oftentimes students do this, things like this, 2/3 plus 4/5, and they cross multiply these and they get 10, 12 something that doesn't work. So remember, only cross multiply in the equation. Now cross multiplication, AD equal BC. That's what cross multiplication is. You multiply the A and D, we call them extremes. So these are extreme. Each of them is extreme. So these are extremes. B and C are referred to as means of the proportion. To have a true proportion, product of means has to equal product of extremes. Okay. Now, if I multiply the means and extremes here, the means multiply to 3, extremes multiply to negative 2x, divide both sides by negative 2, and you get negative 3/2. Notice these are the same. So you can do it either way. So we have one solution there. The other solution comes from a half. 1/2 equals x to negative 1. So 1 over x is half. Flip, 2 equals x. And there you have it. Our domain was as long as we don't have 0. And neither of these answers are 0. So both of them should be a working solution. The solution set is negative 3/2 and 2. All right. And now what about, let me make something like this. Suppose I have something like 12x to the 4th, negative 11x squared plus 2 equals 0. Something like this one. Now, remember, we let the middle term, the variable on the middle term be u. So we're going to let u be x squared. Okay. And if that's the case, you square both sides, you get u squared is x fourth. So this is going to be 12u squared minus 11u plus 12 equals 0. And now we can factor this one out. I'm going to go 3 and 4. Now, middle term negative, product positive, so that means the two numbers are negative. I'm going to go -2, -1, and well, let's see, the product's got to be 12, right? Oh, I'm sorry, but no, I just repeated the 12 here. It's a 2, not a 12. Okay, so I'm going to go -1, -2 like that. Again, I know I have the first and the last, right? The question is the OI. This is the O, that's the I. Oops. This is the O, and this is the I. Outside, inside. -6u, -4u is -10u. I have -11 in here. That didn't work. Let's change. It's close. I'm just going to make this 1 and make this one 2. That should work. 8 and 3, 11. Perfect. Yeah, and that's the factored form. Therefore, 3u minus 2 could be 0, or 4u minus 1 may be 0. And these you can solve. They're linear equations. Add 2 and divide by 3. Add 1, divide by 4. And now we can substitute for u into here. Now this is a polynomial equation, right? 4th degree polynomial equation. So the domain is all real numbers. For polynomials, their domain is always all real numbers. So let's try now. X squared is equal to 2/3, or x squared is equal to 1/4. I'm plugging into what I let x be, or x squared be, or what we let u be actually. Now to solve this, I can go to square root property. Remember, we need to do plus minus 2/3. And on this one, x is plus minus square root of 1/4. Now square root of 1/4 is a half, right? That's like root 1 over root 4. Square root of 4 is a half. Or square root of 4 is 2, so that's 1/2. So there we picked up two solutions here. And we do have two solutions here, but if I break up this one, by the way, as root 2 over root 3. Remember we talked earlier in our review of radicals. We said that the radical in simplest form means a radical isn't allowed to have a radicand that's a fraction. Fraction isn't allowed. That's why I wrote it as root 2 over root 3. And in a fraction, this could be whatever, radical, this is not allowed. We cannot have radicals in the denominator. So I need to multiply top bottom by square root of 3. And remember, square root of 3 is irrational because 3 is not perfect square. And when I multiply top bottom by root 3, 2 times 3 is 6. Root 3 is just 3. Because that's square root of 9 becomes 3. And this is now rational. In other words, we rationalize the denominator. And that we have to do because by convention, that's what the mathematicians have agreed to. So those are our solutions. There are 4 solutions in this one. We have a couple of plus minus root 6. We have a couple of irrational and a couple of rational solutions. There. And that solves this one. Okay. And let's take a look at again some mixed examples now. Something with radicals, for instance. When we did square roots, we didn't do higher roots. So let's say I want to do cube root of 4x plus 3 equals cube root of 2x minus 1. Remember the power principle of equations, so we're going to raise both sides. Because index is 3, we're going to raise both sides to the third power. When we do the left, we have 4x plus 3, and on the right, we get 2x minus 1. There, in one step, that's how we get rid of the radicals. Then subtract 2x, subtract 3 from both sides, divide by 2, and the answer is negative 2. Now, because we have cube root domain of all radicals whose indices are 3, 5, 7, 9, odd in general, are all real numbers. That funny looking R again means real numbers. And negative 2 is one such number, so we're good with this one. The answer is going to be negative 2. All right. And here's the set that holds the answer. Let's do maybe, how about something like, again, simple radical rational exponent that becomes radical. There. Remember, for rational exponents, we raise them to the reciprocal of the fraction that you see. So this is going to be x. Now 125 to 2/3. In order to understand that number, we have to rewrite it as radical. 3 goes in the index, and 2 goes in the exponent, which is, and 125 goes in the radicand. Now, cube root of 125 is 5. 5 squared is 25, so there is a solution. X is 25. Cool. And let's finish this. Let's finish with just one more example. How about, let's say I want to do x to the 4th plus 2x squared minus 15 equals 0. Now to do this one, again, I'm going to let u be the middle term. U squared would be x 4th, square both sides. So x 4th is equivalent to u squared. X squared is u. And there. This should be factorable. U plus 5, u minus 3 equals 0. So u will be negative 5 here and 3 here. Now I'm going to plug in for u here and solve for x squared there. Well, negative 5 equals x squared and 3 equals x squared. Now an observation here, x squared, when you square a number and get negative, that number cannot be a real number, right? But we talked about imaginary or complex numbers, so we should be able to solve this, right? Let's take a look at this one. So I'm going to take the square root of both sides, the square root principle. Plus minus, don't forget the plus minus, square root of negative 5, and you can see there, square root of negative numbers going to be imaginary. So that's going to be plus minus root 5i. That's two solutions. Take the square root of 3 and we pick up 2 more solutions here. So all in all, that was plus minus root 5i outside of the radical and plus minus root 3. There are 4 solutions to this one. And by the way, this some people actually are able to factor this from the get-go. So you don't have to actually introduce that auxiliary or extra variable u. This is what I mean. If we wanted to, we could factor right off the bat. There you go. So x squared, that's x to the 4th. 2 numbers multiplied to negative 15. And the OI combination is 2x squared there. So you can just factor it from the beginning, by the way. That u substitution is optional. It helps a lot of students just to sort of delineate and make it easier. But we don't have to do that. So in this case, there you go. My next step is to just go and solve these with skipping that u variable altogether. And there, plus minus root 3. See how it works just as good. X would be plus minus root 5i. This is without going through that additional variable u. And there we have it. So, again, we managed to do this under an hour. I'm trying to keep the videos to under an hour as much as possible, or at an hour. So there you have it. Hopefully everything made sense. If not, please go back and review. What we just did was solving other types of equations. Thank you for watching.